Hello, everybody. This is our second week, week 9 for the MECH468 and the 949. So last week we mentioned about the modeling of a digital control system inside a computer, which is difference equations. And we had a look at how to actually solve that difference equation and look at the Z transform, which convert from time domain digital system into a frequency domain model, which we then can do a transfer function of the digital system. This week we're going to focus on the two things that additional to the continuous time system, which is the sampling mechanism. So this is analog to digital components, and zero order hold, which is digital to analog components. So this two is the additional parts that does not exist in the continuous time system, and we're going to look at what problems it introduced. So this is kind of we're trying to analyze the mathematical model for those two things, and then because there's additional issues, then we introduce the compensation methods for this sampling and the zero order hold components. So this is the modeling of a sample data system or digital system. So we can see in the middle, this is our computer, which we mentioned last week. This is a computer program. It's partial. It's a difference equation. Then here is our traditional control target object, which is the plant. And in between, we got a sampling mechanism, which we got our feedback signal and take some samples. Also, our reference signal will take some samples, and both of these samples goes to the computer. You get continuous time signal become a sampled signal. And after this calculation inside the computer, we have the control signal, and this control signal needs to turn into a continuous time signal. So this is a sample, KT. So at different instance of K, you got slightly different values. And this component called a zero order hold. This is one type of kind of digital to analog converting mechanism. So last week we mentioned all this in the between. This week we're going to mention sampler and signal reconstruction. From the beginning of the control theory subject, we already mentioned there's a very interesting signal we call a delta function. So this is a very special signal with when time equal to 0, you got an infinity. So if I draw the figure, so it's this blue one. When time equal to 0, this delta t is infinity, and it's 0 elsewhere. So basically it's just a pulse, a very large pulse at the time 0. Another restriction for this direct delta function is the integration of the signal equal to 1. So basically if you calculate the whole area under this function, is actually you get 1. So let's keep these two in mind, and we can actually multiply this direct delta function onto a certain signal. Say a signal is xt. Say we have a signal xt. This is our signal xt. So multiplication of this signal with a delta function, because every elsewhere is 0, and you only have that part is non-zero, and because this integration is 1, so actually you're reading this is exactly x 0. It's showing up here. Mathematically, we can have a look at here is xt delta t. If you integration this xt with delta t over everywhere, what you got is because here the delta t only has value at 0, so every other xt doesn't matter. You only have x0 here. So basically you have constant. Then if we take the constant outside, take this outside, you got this x0 multiply with the integration of delta t from negative infinity to positive infinity. And this is equal to 1. As we see from there. Okay, so actually what you got is just x0. So this basically looks like take a sample of the xt at time equal to 0. And some property for this unit impulse signal or delta signal. If we have this delta signal not at 0, rather at time equal to large or capital T, okay? And this delta signal can be represented by delta lowercase t minus the capital T. The capital T is just constant. And if you have this delta signal, and we look at any signal xt, multiply with this signal, you actually got that xt value at this instance. So you got this. So basically this is called a shifting property. If you're shifting the delta signal by a certain time, you are taking a sample of the original signal xt at a different time instance. A useful application is in the frequency domain. Remember, all we mentioned here is all continuous time signal. Okay, or the xt, delta t, they are all continuous signal. So let's look at the signal in frequency domain. So we do a Laplace transform of the delta t. This is our delta t with shifting with capital T. So this is basically Laplace transform. Okay, you do the calculation, what you get is this e negative j omega t. And remember, we know in the S domain, the time delay in S domain is e negative s t. That's our time domain in S. Time delay in S domain. Okay, so did you see any similarity here? The difference basically if S equal to j omega. Okay, so normally in complex plane, S equal to sigma plus j omega. That's the real component and the imaginary component. But in here, or in many signal processing applications, normally this real part is just 0. Okay, so you can see replace the j omega with S, or replace S with j omega. This is the time delay in S domain. So basically this unit impulse, or this delta function with a shift in t is a time delay with that t. Okay, so this is something become very interesting, and we can use this. So we have one delta function, and how about we have another one with a delay of t, have another one with delay of 2t, and so on. And we add them together, so we have a train of delta signal, represented by sigma delta t minus kt. And then our original signal is xt. What about we multiply these two together? Okay, pretty much you got samples at each one of this whenever you got a delta t. Okay, so this is exactly what's happening with the sampling. And mathematically, what's happening is you get a x star t, which is xt. That's the original signal. That's the original signal. And then multiply with delta t minus kt with sigma, because this is the chain of those samples. Okay, so this is a sampling. And this is the original signal. And if we put this together, we call this star transformation. And basically, this is what sampling do. You get a continuous time signal, and by multiply with this a train of delta signal with offset of t, which is the sampling frequency, we got x star t is the signal after the sampling. And remember, this here x star t is still continuous time domain. You haven't got to say xk yet. Okay, this is digital. At the moment, this is still continuous time, but it's continuous time but with all these individual values. Just the values that doesn't show up, all these other places, just all the zeros, pretty much. And this figure just shows what's happening. Original signal, you multiply with that delta t, a train of delta t, what you got is x star t, which is what we got for the sampling. And this train of the signal, or we call it impulse, train of the impulse, is represented mathematically like this. And the output xt is, or x star t, is basically the input signal. Well, here we change the xt. We change the xt to xkt because it's 0 as well. Doesn't really matter. And this is our sampling operation. So do a summary. So sampling basically is the original signal multiplied with a train of delta signal. Okay? And we got a new function called x star t. This is by sampling of xt. And each one of these sample, the delta signal, is delayed by a t. So that's our sampling frequency. And xt only got value at the sampling moment. It will be 0 as well, or between those sampling moment. It's a train of impulse signal. And the strength of each one of these signal at x star t represents the value of xt at that moment. So this is perfect, right? This is exactly what we want. Now let's look at the Laplace transform of this ideal sampler. Okay, why can we do a Laplace transform? Because this sampler, this is a time domain, is still a continuous time transfer function, you can call it. And let's see what's interesting about Laplace transform. So this is the definition of Laplace transform. We just replace the whole thing in there. So we got sigma k from negative infinity to infinity, xkt, delta t minus kt, put in there. We got this one. So it looks quite complicated, but this is a integration of lowercase t and the summation of small k. Okay, so if anything irrelevant to lowercase t can be taken outside of the integration. So this whole bit has nothing to do with lowercase t. So we move that outside. What's left inside is this. Okay, remember in the last slides we look at the sigma t, the sigma t and sigma t minus t kt. What's its property? It's time shift. So this whole bit actually is equal to E negative SKT. Okay? So this basically, you can see what happened here is the Laplace transform of the signal is the signal itself at that sampling moment with a time shift. Okay, so even you adding this together, they won't be able to add because they add different time instance. This one is basically just different time instance. You can't actually add them together. And we compare to the Laplace transform of the continuous signal. Okay, this is the Laplace transform definition. Okay, do you see anything similar here? Okay, what this one compared to this one? So this is sampling, and this is a Laplace transform of the continuous time signal. Quite similar, right? One is the summation, and the other one is the integration, and S just becomes KT. Well, ST becomes SKT. So this two is very similar. And this actually linked to Z transform, if you still remember. So that's XS star. If we just replace Z equal to E negative EST over here. So XS star becomes XZ. We replace negative negative still there, just ST. E power of ST is become Z power of K. Okay, so just replace Z equal to EST. And this is definition of our Z transform. So there's not we're just lucky. This is mathematically linked to each other. So if we look at this thing we mentioned last week, Z minus 1 is a time delay. Okay, so we know EST is a time delay. So these things are just one in continuous time, one in discrete time, but they are the equivalent stuff. And this is its representation. And we look at Z transform. Okay. Each one of this is its time delay. Okay, instant delay with a sampling time. And this is actually its value of the original signal. Okay, so we bring things together now. The Laplace transform and Z transform, we can simply link them with this, but not all the time we can use it. Okay, in most situations, when we convert from one to the other, we can use that. That's how these two things are linked to each other. But remember, it's not just as simple as that. Particularly when we do some system design, this kind of mapping address quite a lot of problem, but still it's not the only way to do it. And in most cases, this is not the right way to do it.